Hello guys, thank you so much for being with me in another machine learning tutorial video. In the previous videos we talked about neural networks, so we said that if we want to train a very large neural network, we can use advanced optimization methods instead of the gradient descent algorithm. Be sure to work with different methods to get to know the details of this. In more advanced calculations, we prefer that the cost function returns both the error and the gradients. If we have a two-layer neural network, we have W1, B1, W2, and B2. But in the implementation code, we have only one vector. So we combine all of these vectors and turn them all into one vector. Here we have a series of matrices W1, W2, B1, and B2. All of these must be converted into a vector. What we do is first level the two matrices W1 and W2 because they are two-dimensional. First we have to make these one-dimensional, and then we can concatenate them all together. Now we need W1, W2, B1, and B2 in the loss function itself. That means we have to separate them again. To extract W1, W2, B1, and B2 from the long vector W, we can say according to the sizes, grid structure, and storage order, extract from the WA matrix from the beginning up to the, for example, F multiplied in H element, and convert it into an F multiplied in H matrix. In this way, we extract the rest of the matrices. After the extraction, we perform the quantification randomly. We value the biases with the zero matrix. Finally, result, we store X inside the matrix W, and we have to differentiate it again. If we do not define the Jacobian, the algorithm calculates them in an approximate way. We may have made a mistake in our analytical calculations. The basis of a neural networks is gradients, and we must make sure that you have calculated the gradients correctly. We use both methods to test the correctness of the gradients, both the analytical method and the estimation method. If our calculations are correct, these two values should be almost equal. When we are sure that everything is correct, we will save this part as comment because it is very expensive. In mathematics, the definition of differential is a one-dimensional function, so was like something that you have seen during the years of studying mathematics. What we do is apply the formula. We apply this formula to the elements of the vector W one by one. In this way, we estimate the gradient at the point W1 in the direction H. We repeat this for each element. Finally, we get the dW vector. Here I have put the implementation of the same explanation for you. This is an approximate method One drawback is that its accuracy is highly dependent on age, and the second problem is that it is very time consuming. We use this method but only to test the correctness of the analytical method, and otherwise we do not use this method at all. So far we have seen the gradient descent algorithm. There is a case of gradient descent where we estimate costs from a small subset of the data. First we need to select a small subset from the training data. In recent years we have realized that the smaller they are, the better. The optimal size is 32 or 64. Only based on this small subset we estimate the gradients and then perform updates based on this estimate. I have already explained the types of gradients. If you have class C, initially the softmax value should be equal to log. You can see that over time with the increase of epochs the amount of the cost function is decreasing. All these implementations are in Python files and you do not need to memorize them. Here we only mentioned the principles and concepts of neural networks as one of the best machine learning techniques, but these are not all neural networks. In the specialized training course on neural networks, I explained in detail the different types of neural networks. In the continuation of supervised learning methods, we go to support vector machine algorithm. We can solve the most difficult problems in artificial intelligence using neural networks, but the main motivation for using other methods such as SVM, which stands for support vector machines, is to find the optimal decision boundary. First, we review a series of basic concepts, then we explain the objective function. We see linear and nonlinear categories and explain what tricks there are in case of nonlinearity. This kernel trick can be used in many other areas of machine learning in addition to SVM. Then we go to the multi-class categories. Therefore, despite being a very useful method, this method also helps to understand the rest of machine learning concepts. This method became most popular since 1992. This method is one of the most popular machine learning algorithms. Those who want to work in the field of machine learning from non-computer fields are very much in favor of this algorithm because it is much easier to use, because there are no hyperparameters. The implementation of this algorithm is not at all simple, but these are much easier to use. They perform cleaner classification than other machine learning methods. Okay. This method is not specific to classification and is also used in regression. This method can be used in data that are linearly separable and can be categorized with a single line. In the n-dimensional space, they can be grouped with a hyperplane and hyperplane classifier. But is this the best decision making boundary? Is there another new criterion that goes beyond accuracy and correctness? We can draw an infinite line whether these have no difference or there is a difference between them. For example, between these two images, the left classifier is preferable because it has better generalization capability. We have only selected a small subset of the training set for estimation, and there are maybe other similar data that are misclassified in this image on the right. The idea of SVM is that it selects the classifier that has the most overlap with the data. Since the data is the real world also has noise. If this margin is too small, the classification may be wrong. The distance between the classifier and the data of both classes is called margin. If you use neural networks, the best decision boundary is not necessarily obtained. The width of this highlighted area is called margin. We now have two goals. We also want the data to be classified correctly. In addition, we want to maximize this margin. First, we must define this goal mathematically. Here, the most important data are the closest data from all classes to the classifier line. We choose a name for this data. The name of this data is support vector. These are the determinants of this margin. Shifting these can change the best decision boundary, but moving other data does not have the same effect. Having this support vector, we can write the equation of this decision boundary. W is no longer a vector here because our space here is two-dimensional. W is a number. B is an even number in the multidimensional space. When the decision boundary is a hyperplane, W will be a vector, but B will still be a number. Sometimes this method is also called the categorization with the largest margin. Again, we want to find the parameters so that both the data are correctly classified and the distance of the decision boundary to the support vector is maximized. The text changes again. Here we have xt and yt. Which are all samples in the training set. Until now, when we had two numbers, we considered the one class as 0 and the other as 1. From now on, when we have two classes, we consider one class as a positive one and the other as negative one. You can see further how much this change contributes to the simplicity of the algorithm. We have already said what the decision boundary line equation is. You can see that the concept is better understood by naming it a positive one and a negative one. It is as if we have a margin equal to 1 on both sides of this border. Class data must be greater than 1, and that is the value of W transpose X plus B for that data must be greater than 1. Likewise, we say that the value of W transpose X plus 1 must be smaller than minus 1 for class minus 1 data. For that data, we can again combine these two equations. We multiply the sides of the equations by YT. In this way, both equations become one equation. The support vectors are the data that these dotted lines have crossed. This margin width is what we want to calculate. When the points are placed on the line T, and this line, it means that their coordinates apply to the equations of the lines. We subtracted these two equations. So finally we are looking for the smallest w that will definitely do the classification correctly. To maximize m, we must minimize w. These problems are called the constraint optimization problems. We want to do the minimization, but on the condition that the classification is also done correctly. Minimizing the size of w is no different from minimizing the size of half the second power of w. But half the second power of w is a convex function, so it will definitely have a global minimum that can be reached. We will postpone solving this optimization problem to the next video. This solving process will be explained in the next video. Don't worry about them. We do not perform this minimization because implementing this process is not easy at all, but there are ready-made implementations that we can easily use. I again highly recommend you not to miss the upcoming lectures because of many practical and important tips inside them are awaiting for you. Have a nice time.